One test down, that.
Yeah.
I was doing problem simple number.
Yeah.
3. And I was trying like the same like, steps like on the notes.
Yep.
And then at the end, I'm not sure if I'm supposed to like all this and have it like a coefficient over here.
Okay. Yeah. So I mean, it's all the equations that you get, they're all, relative up to a scaling constant. And so what some people are doing is you kind of divide the whole thing by 5. That's going to divide this whole thing like that, and that's the same. Too. And so one thing that you can do is that you can look at like. Usually the diagonal terms are usually pretty easy to look at. And so if you scale everything to try to make your diagonal terms the same as then all the other kind of scaling factors come into play. But for this one specifically, I kind of messed up, and so I kind of made the diffusion coefficient a little bit too high. And so this one's going to be stable with the central difference. So I think I said appropriately stable. And so this one's actually stable with central difference. I actually want it to be unstable with central differences. So this one, if you want to match my coefficient, you probably need to use a forward difference for the convection. Yes.
Oh,
Yeah.
okay.
Yeah. And so that might be another reason why the scale.
Oh, okay. I was like, so I was like doing it right, and like when I got to your answer, like didn't match up, and
yeah, I try to do things like this so that I have like nice whole numbers, because like decimals here and fractions they're a little bit harder to work with, or to me they're aesthetically a little bit harder to look at, and so I try to make whole numbers here, and then I try to make decimals of it. That's generally my but it doesn't have to match exactly that. And so like if you took my solution and you divided everything by 5, then you would get different coefficients, but then these would be different as well. But that would still be correct. You still end up with the same p value because everything is scaled by the same.
Yeah. And then
and
I went
another
with
question like to get like the matrix.
Yep.
I'm supposed to plug in like every point, right?
Yep.
To the equations.
Yep.
Okay.
Yeah. So each node has a different export that you plug in.
I'm gonna retry it.
Okay. Yep.
The equation I did, I put the numerator, I did the angle.
Yeah.
It should have been here also. Because like you do the equation equal.
Yeah.
On the table. Yeah, so it should have been like angle plus 1.
Oh,
it shows up on the table it's a plus, it's plus, which is weird. Because it's like on the one where you it's the exact same thing I was looking at, and I was like, that equation's wrong. It's on the notes, it says plus, it says gamma plus 1.
Yeah.
But it's like on the one where it says gamma minus 1. So I just used the one from home. And I ended up getting to remove the table.
I usually don't have like all the on fixes, but like I messed up, like.
Yeah.
Yeah, but even then, like you see the process that you went through. So
Yeah, that's true. It's some.
what was it? Gradient flow, right?
Yeah.
So you're using minus 1. Use this one.
Yeah, so I like, when I plugged it in, I plugged it in wrong, so I didn't get a minus.
And then you got the number on the table. Huh?
Yeah.
It's because on the homework he did that.
Yeah, so.
He used minus 1 instead.
I just did a ratio, so I didn't apply anything on that right side. I just got the actual value of the temperatures divided with the process of it, and with that I just.
Well, that's what you're
That's
supposed to
what
be,
you're
but getting the,
Yeah.
is what, like, you needed the money.
Yeah.
So, We're done now.
It's
over.
I got you.
I'm pretty sure, regardless, the one that was closest, because I did it both ways too. Regardless, the one that was middle one. The one where it was.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Hello.
All right.
You guys had just had a midterm, looks like.
Yeah.
It's always. How was it?
Not too bad.
It was
Not too bad.
fair.
Okay. Okay, well, it's done. That's the always important part, right? A lot of negative experiences, they end eventually in your life. So, and that goes the same for midterms as well. Okay, so today we have just a little bit to finish up with convection, but not too much. And then we're going to move on to something new. Okay, so let me write something first, just to kind of just because I know this everyone's going to ask this. If I can spell toddy. So today's lecture, not on midterm. Okay. And so I know we have a little bit, just a tiny little bit to finish up on convection. But I've already written the exam, and so that part's not on the exam. So you don't have to worry about it. Yeah, so the exam's going to cover up to Monday, basically. Okay. And remember, our midterm is next Wednesday. And so make sure you are present for that. And so there's no plans to offer the exam virtually. So please make sure to come in person. Okay. You won't need any MATLAB for the exam, but I do recommend that you bring a calculator just to help you with some of the calculations. Okay. Okay. And I think that's all my announcements. And so are there any questions on anything before we get started for today? My day, it's good. Yeah, just a Wednesday. I haven't given any exams yet, so all my exams I usually do a little bit later, and so I think next week is the week everyone's going to hate me, but I'm ready for it. Okay, all right, so let's go ahead and get started then. And so we have just a little bit to finish up from the lecture on Monday, and that's the idea of cross-stream diffusion. All right. And so if you recall, we did kind of an experiment at the end of class last time where I gave you a working code that solves convection diffusion in 2D, right? And we saw something strange, right? Because what we know from our 1D convection diffusion is that when we compute the Peclet number, okay, where the Peclet number is the velocity multiplied by the grid spacing divided by the diffusion coefficient, okay? And if we are running a central difference scheme for convection, okay? If we want to use a central difference scheme for convection, we know that our Peclet number has to be less than 2 in order to get a stable solution. Right? Right. So we tested this in 1D, and we saw the results of what happens when you don't have this, right? And so when you don't have this, then you get an unstable solution. But we did something interesting in the 2D code. And so in 2D, what we did was we set our x velocity to be 1,000, okay, and our y velocity to also be 1,000. Okay. And we had already seen, when we set just one of these to 1,000, so I believe we set y, the y velocity to be 1,000. We already got an unstable solution for our 2D code. Okay. And so what we expected is that when we set both the x velocity and the y velocity to 1,000, we should get a very unstable solution. Okay. But the reality was something different. So the reality was I wouldn't say it's fully stable, but I would say it's mostly stable solution. Okay. And the question is why, right? And so why is it that, when individually, if we set the velocities equal to 1,000, they end up with a unstable solution. But why is it that when we set both of them to 1,000, we end up with something that's mostly stable? Okay. And so the reason for this is a phenomenon known as cross-stream diffusion, which is a phenomenon that's unique to 2D convection codes. And the reason for cross-stream diffusion looks something like this. And so if I could draw our grid right here. Okay, so this grid here represents our domain. Okay. What can happen in 2D? What can happen in 2D is that our velocity can be unaligned with the grid. Okay. And what I mean by that is that the velocities don't follow the grid lines that are given here. Okay, so notice our grid lines, they run vertically up and down, and they run horizontally left and right. Okay. If we have a situation where both the x and y velocities are, x and y components of the velocity are 1,000, what happens then is the velocity looks something like this. Okay. And so, in other words, the velocity is not traveling, the fluid is not traveling along kind of the grid lines that we've kind of preset for it. Okay. Right? And when this happens, and we won't get into the numerical details about why it happens, but I think it's important just to know the result. What ends up happening is that the diffusion coefficient gets artificially increased. Okay, and so the key word there is artificially, because it's an increase in the diffusion coefficient, but it's not something that we want. It's something that just it just happens as a result of the mathematics. Okay. And so we can compute this, or at least a rough approximation of this. Okay. Okay. And so I'll go ahead and define it as K false, where K false here is our artificial diffusion. Okay. And so artificial diffusion is given by, first we take the magnitude of the velocity. Okay. And so you take your two velocity components, you take the magnitude of it. Okay. Then you're going to multiply it by the grid spacing in the x and y direction, so delta x, delta y. And then you're going to multiply by sine of 2 times the angle. Okay. And I'll define the angle in a second. Okay. And you're dividing it by that monstrosity kind of on the bottom right there. Okay. The exact thing doesn't really matter. You know, it's not something I'm going to ask you to compute on a regular basis. But you know, this for this formula here is just kind of there for your information. Okay. And so the key quantity here is theta. And so theta here is the angle between the velocity vector, oops, and the grid lines. And so in our case, you know, we have a velocity vector that has, you know, 1,000 for the x component, 1,000 for the y component. And so our velocity vector looks something like this, okay? Okay. And so if we were to take the angle between that and one of the grid lines, and so let's take the horizontal grid lines, okay? In our case, you know, if you have a vector that looks like that, you'd have a theta is equal to 45 degrees, okay? Okay. And if theta is equal to 45 degrees, you can see that that's the theta that actually maximizes the equation above, okay? And so since you have sine 2 theta, we know that sine is a maximum when the argument within sine is 90 degrees. And then in order to get 90 degrees on the inside, for this equation, theta has to equal 45, okay? And so the more, basically the more misaligned your velocity is with the grid, then, you know, then the more this artificial diffusion kind of kicks in. And so this was the reason why we got a stable solution, you know, when we cranked up both the x and y velocities to 1,000, because it basically made this artificial diffusion here, you know, really, really large. Okay. And so the total diffusion coefficient is simply the sum of the original diffusion and this false one. Okay. And so that's usually not a good thing, because usually when you're solving these problems, or when you're computing solutions to these types of phenomenon, you're setting your diffusion coefficient, you know, usually with some thought. Okay. And so let's say for instance that you're using our codes here to solve the heat equation, right? And so for the heat equation, your diffusion coefficient is exactly your thermal conductivity, right? And so the thermal conductivity is usually something physical that you're going to be looking up in a data table. And so you want to maintain that same thermal conductivity throughout the entire simulation. And so if you have a situation where your thermal conductivity is artificially being increased by something that's not physical, so this is not a physical thing, this is purely a numerical error, then that's not good, because then the solution that you're computing is not accurate, because you're not representing the thermal conductivity correctly. Okay. And so this is a big issue. And so you know, whenever you have convection in 2D and this effect is magnified in 3D as well, you need to take care to address this if it's there. Okay. Question is, how do you address it? The same way we solve every single problem in this class. We just refine the grid. Okay. I know it makes it sound easy, but really refining the grid kind of makes a lot of problems go away. Of course, at the cost of making your simulation more expensive. Okay. And so since you have a delta x, delta y in the numerator, you can mitigate the effects of artificial diffusion by just simply refining your grid. Okay. Any questions on this? Okay. Okay. And so just to sum up convection, you know, just because I want to make sure we, you know, we kind of have a nice summary before we move on. You kind of have two options when you're simulating convection with finite differences. on the one hand, if you want to go for pure accuracy, you can use central difference for everything. Right? And so that includes the convection derivatives. The good thing about central differencing for the convection derivatives is that you obtain second order accuracy. Okay, so second order accurate is good. But the downside for central difference is that you run the risk of going unstable. And so that usually happens because your grid is too coarse. Okay? And so if your grid is coarse, then your Peckley number is going to be very high. And if your Peckley number is very high, it's going to lead to an unstable solution. Okay? Right. The other approach that you can take is upwinding. And so if you take an upwinding approach, the positives to an upwinding approach is that you end up with a stable solution. Okay, and so a lot of times that's good, and so you don't have to worry about instability at all. Right. And remember, the reason for that is because upwinding, you know, the reason the way we chose the weights for the different terms matches a lot more closely with you know, with the physics of the problem. Okay. Yes, yeah. So upwinding was putting more weight on the upstream, and so that's either using a forward difference or backward difference, depending on which direction the velocity is going. Yeah. Okay. But the downside to upwinding is that you end up with a scheme that's first order accurate. Okay. And so if it's an application where you want to have more accuracy, then you know that's something to be aware of. And so with the first order accurate is not bad, and so you know it's not a bad thing. But if you want to get an accurate solution with the first order scheme, you're just going to have to work a lot, just that much harder. Okay, and so you're going to have to refine your grid even more to get accurate. Okay, and so it kind of seems like no matter which way you choose, you know, the answer is just to refine your grid. So the more you refine your grid, then you don't have to worry about instability, and you're going to have an accurate solution, and that's true, right? And so that's never not going to be the answer in this class, is to find your grid. But of course, it's all about how much cost can you tolerate. Okay. You know, I mean, the most extremes that we'll get in this class, you know, for the final projects, I've seen some people's codes take about an hour to run. But for more practical cases, you know, it could make the difference, you know, whether you use a refined grid or not, whether your simulation runs in a day or a week. Okay, and so that's kind of where it stands. Okay. All right. Any final questions on convection before we move on to unsteady problems? Okay. All right. So let's go ahead and talk about unsteady problems. And the algorithm that we're going to be using to solve unsteady problems is called time marching. All right. And so let me start this off by saying that, you know, so far we've covered kind of the two main transport mechanisms. Okay. Okay. Those mechanisms being diffusion and convection. Right. And so there's no more transport phenomena, you know, at least not in the heat equation. Okay. And so, you know, heat and energy can only be transported through diffusion and convection. Okay. So we're not introducing any new physical processes. Okay. But what we are doing is essentially relaxing one of our assumptions that we've been making. Okay. Okay. And that assumption was the assumption of a steady state solution. Okay. And so the result of this assumption was essentially that all of our solutions were only functions of space. Okay. And so our solutions look like this, where, in 1D we have phi as a function of x, or in 2D, we have phi as a function of x and y. Okay. Okay. But the real life isn't a steady state situation, right? And so the world is changing every day, in more ways than one. But also, heat transfer and transfer phenomenon also change with time, and so we need to be able to solve for such cases. Okay. Okay. And so to do this, we're going to modify our conservation equation to include that unsteady term. Okay. Okay. And so now our conservation equation is going to look like this, where we have partial phi, partial t, plus u, partial phi, partial x. And I'm just going to do the 1D case right now. Okay. And then we'll generalize this to 2D, later on. Okay. Okay, so let me go ahead and label these guys. And so our newest addition is this derivative with respect to time. And so this represents unsteadiness. Okay. This here represents convection. Okay. Then of course our second order derivative is diffusion. And our Q here is our source as usual. Okay. And so, the gang's all here now. And so, we're not leaving anybody out anymore. We're going to solve this equation in its entirety. Okay. But the reason I save time marching to last is because time is just very fundamentally different than space. Okay. And so how we solve these and how we approach solving these needs to be different as well. Okay. We're still going to use finite differences, but we're going to kind of apply it in a little bit of a unique way. And so the class of algorithms that we're going to use for this, that transcends actually just finite difference in general, is called time marching. Okay, and that name kind of has a very specific purpose, or you'll see what I mean by time marching. So we start talking about the algorithms. Okay. Another important consequence, and I think this is the coolest part that I think people will generally like about this unit, is that the nature of our solutions are going to be different as well. Okay, And so up to this point, when we were solving steady situations, our solution was just a static image, right? And so it was a steady image of either a 1D plot or a 2D color plot. Okay. Because our solutions here are changing with time now, then our solution is no longer just going to be a still image, but you can actually splice all the solutions together into an animation or into a video. Okay. It's funny that you would ask that. So the question is, so you can actually simulate how a fart will travel in a room. That was actually the final project last year when I taught this class last year. So I had them simulate that exact thing. You had a room and you had a gaseous substance. I didn't call it a fart. I called it a gas leak. But you can interpret it as such. So unfortunately, I ran that project last year, and of course it was fun, but you guys are gonna do something different for the project this year. Okay. And also just a little bit more terminology, and so we're gonna need some new conditions as well. Okay. Whereas before, we only worked with boundary conditions, but boundary conditions are only applied in space. But since we're going to be solving problems in time, we're also going to need initial conditions. Okay. And what initial conditions are is they define the full solution, what it looks like at a specific point in time. Okay. And so we'll go through the specifics of that, once we actually get rolling with this. All right. Any questions on any of this? Yeah.
With respect to the solutions will change with time.
Mm-hmm.
Is that also because how the vectors have multi variables?
It's not the vectors that have multiple variables. It's just that our solution itself, it'll change its value over time. And so I think it'll be a bit more clear once we start doing some examples about what that looks like. But MATLAB, but basically we're going to be writing MATLAB code to be producing GIFs. Basically, you can think about that. Yeah. Mm-hmm.
Oh, so that's a produce a video.
Yeah, we're going to produce videos in MATLAB. They're not. I mean, of course, I think they're cool, but then it's probably not something cool enough to show on social media. I'm not going to stop you if you think it's cool enough. Then by all means. But I don't want to hype it up too much. That's my main thing. Okay. All right. And so now that we kind of have the motivation about how we're going to do this, let's talk some notation, because that's going to be really important. Okay? Because now that we're going to be considering solutions that change with time, we need to change up our notation a little bit. Okay? Okay. And so before, the only notation that we really had for our solution values was what I would like to call IJ notation. Okay. And what the IJ told you was basically where a specific node or a specific solution value was located, right? All right, so now that we're dealing with time as kind of like an extra dimension to our problem, we need another index to take care of to handle that time. Okay. And the variable that we're going to use this is do this is called n. Okay. And so from now on, when we're doing unsteady problems, when I write a phi value, it's going to look something like this. Okay. And so just like before, I'm going to put the ij spatial location in the subscript. Okay. But in addition to that, I'm going to have a superscript that denotes the time index. Okay. Or in other words, when this solution is taking place with time. Okay. All right. And in particular, there are a couple time indices that are important to note. Okay. Right. And so when I say that we're at time index n, this is the current time. Okay. Current time being the time at which we're solving for the solution right now, okay, or the current time that we've already solved the solution for. Okay. And most of the times, once we moved on to time step n, we already know the solution at this time. Right. And so we've already performed a step of our time marching, and so we know what the full solution looks like at time n. Okay. Right. This is in contrast to n plus 1. And so n plus 1 is what I like to call the next time. Okay. And so the next time is the solution that we're solving for in the next time step. And so this is usually what we're solving for at each step of our time marching. And so at this point, usually at this point in our time marching, our solution is unknown. Okay. And so this distinction is going to be important, and especially it's going to be especially important in interpreting some of the methods that we that we're going to be using. I know this all seems a little bit arbitrary right now, but this and usually I don't like to introduce kind of what I like to call jargon at this point, because we haven't really gone over the methods yet. But this is one of those cases where you kind of need to know this kind of before we get started. And so I haven't really given much context to this, but just know that when I refer to time step n, that just means the current time when we know the solution already, and then n plus 1 just means the next time. And so that's what we're going to be solving for next. Okay. And so these time marching algorithms kind of progress sequentially. And so first of all you start with your initial condition, and so your initial condition is your first known solution, and then you use your initial condition to solve for the next time step. And so at n plus 1. Okay. Then what you're going to do is you're going to take that solution at the next time step, okay, that you just solved for, and then use that to solve for the next one. So it's kind of like this kind of a sequential thing that goes on. It'll make more sense once we do it, but that's the reason why I'm introducing this notation now. All right, any questions on this? Okay, all right, so let's go ahead and jump into the methods. And so there are two main categories of methods that we're going to go over in this class, or just two methods. But these two methods can kind of generalize to a lot of other time marching schemes. Because in reality, there's dozens of them out there. But these are kind of the two most basic ones, and I think the two that kind of illustrate the respective properties of their category really well. Okay? And so the first method that we're going to go over is called the explicit Euler method, or explicit Euler, depending on how stuck up you are and how you pronounce his name. Okay? I don't care. You can, I've heard Euler, Euler, whatever makes the most sense to you. And so this is a popular choice. And so when people are first learning about time marching, explicit Euler is usually the first one that people learn. Okay. And so in terms of complexity, this is not that complex. Okay. It's simple, but it's surprisingly very effective for how simple it is. Okay, and so to get the explicit Euler, we're going to be starting with our general conservation equation. Okay, and so our general conservation equation, remember, was partial phi partial t. So what I'm going to do is I know normally the convection term is right here, right? So normally the convection term is right next to the time derivative, but just because it'll make things a bit easier next time for the next step, I'm going to go ahead and move that to the other side of the equation. And so if we move the convection term to the other side, what we have is a minus u partial phi partial x plus k partial squared phi partial x squared plus q. Okay. All right, so this is the equation that we're starting with. Okay. And you know the drill at this point. And so whenever we see a differential equation like this, what we want to do here is we want to discretize it. Okay. And so by discretizing, I'm going to replace all the derivatives here with a finite difference approximation. Okay. Okay. And we have three derivatives here. And so I'm going to be a little bit explicit here and say which schemes we're going to use for each one. Okay. And so first we have the unsteady term. Okay. And so for unsteady, we're going to use a forward difference. In time. Okay. So that's going to be in the in time part is important, and you'll see what that means notationally in a bit. All right, so for the convection term, I'm going to do a central difference. So we're going to assume that we have a low enough velocity or a low enough grid spacing. And so the difference thing we're going to do for the convection term is central difference in space. Okay. Right, and then for diffusion, we only know one way to discretize the diffusion term, which is just central difference. Central difference for a second order derivative. Okay, and of course, this is going to be in space as well. Okay, so let's go ahead and do this. And so let's start with the unsteady term. Notice how I said we're going to take the derivative in space, in time, excuse me. Okay. So normally when we take a finite difference, we use I plus 1, I minus 1, stuff like that. But since we're taking the derivative in time, I'm instead using the time index, which is our superscript n. Okay. And then I'm going to divide it by delta t, which is the time step size. Okay. Okay, then we have the convection term, which we are doing central difference with. Okay. Okay. Right, and so for our diffusion term, we have our usual, central difference scheme, and then we have our source term. Okay. All right. Let me give people a chance just to write that down. Okay. All right, so there's a lot of indices floating around here. So let me make sure and to kind of explain every single step here. Right. And so just like I mentioned, as we were writing this down, for the time derivative, notice how I've made the indices n+1 and n because we're taking a forward difference in time. Okay. And so when you take a forward difference in time, that's what that means. And so you take, you increment the, the time index, not the space ones. Okay. But more importantly, since we're only taking the derivative in time, I left the spatial indices alone. Okay. And so the spatial indexes for the time derivative are still I and I. Okay? So I didn't do any I+1, I-1 for that because, we're taking that derivative in space. Right, same thing for the spatial derivatives. And so for all the spatial derivatives, you can see that I left the time index alone. And so I left all the time indexes for the spatial derivatives as n, not as n+1. Okay. And so that distinction is really important. Okay. All right. And so now that we have this expression here, let's go ahead and use some algebra and solve it for this guy, because we only have one term that has n+1. And so we can go ahead and solve it in terms of that. Okay. And so what you can imagine here is I'm going to take delta t and I'm going to multiply by both sides. And I'm going to add phi I raised to the n, okay, to the other side as well. And I'm going to rearrange some of the terms just to kind of group them together. Okay. And so, I'm going to go ahead and skip ahead in the work a little bit. But you can go ahead and verify this expression yourself. Okay. Okay, so I'm skipping the algebra. And so if we skip the algebra, we get the following equation. Okay, so we have phi I n+1 is equal to u times delta t divided by 2 delta x plus k delta t divided by delta x squared. Okay, this is multiplied by phi I minus 1 to the n. Right, then you have 1 minus 2k delta t divided by delta x squared, the sub I at the n index. Okay. Then we have a plus a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared. So this is phi I plus 1 to the n. And then we have a q delta t. So quite a little bit going on. And so, we're taking a little bit of a different approach here. And so we're not, I think usually in the past we divided through by the diffusion coefficient, but here I'm just kind of leaving it all the same, okay? Because the goal here is to solve for phi at n+1. Right. And so if I were to give this formula a name, and so this formula here would be the explicit Euler equation for the solution at the next time step. Okay. Right. And so for actual problems, you of course would plug in for all the values there, and so you would know what the time step size was. You would know what the velocity is, you would know what the diffusion coefficient and the grid spacing, okay? And so it looks quite nasty here, but in most cases you would just plug in for all the numbers and you just get kind of normal coefficients as usual, okay? So the next thing that I have planned here is an example just to kind of show you how it works, because the way that these schemes work is quite different than how we've done it before. And so I want to do just a simple example just to illustrate that. And then I have code that I've actually posted on Canvas as well for you to look at as well. Because I think you kind of have to see it in action in order for it to kind of really click. But before we do that, are there any questions on any of this? Okay. All right. So let's do an example. Okay. And so in this example, I'm going to ignore the convection terms for now, and let's just do an example with unsteady diffusion. Okay. And so our formula for unsteady diffusion is partial phi, partial t is equal to 3 partial squared phi partial x squared. Okay.
This quick question.
Yeah.
So your ed, is that going to be the same amount of like cells, or same amount of
The same time apart from each other.
well, kind of like, because you know how if you're to input things in MATLAB, you need to have the same amount of kind of like dimensions for arrays. Is n going to be the same amount as we do our time increments?
It'll be independent of space, and so the amount of n's is going to be independent of the amount of x points that we have. But that's something that you can specify beforehand. And so that's usually a user specified, how many time steps you want to run if you want to run the simulation for. I think you'll see once we do an example. But usually the engineer or the user decides how many time steps to run.
I guess my question was like, is a time step a second, or is that like
and so you're talking about the delta t, right?
Yeah.
So the delta t is also something that you specify as well. And so it's something that the user chooses. And there's guidelines of how you can choose it. And so it kind of follows the same rules as the grid spacing. So the smaller you have your delta t, the more accurate your solution is. But but everything comes at a cost. And what we'll see here actually too is that for unsteady problems, the issue of stability will become an issue again as well. And so you need to choose your delta t such that you get a stable solution. Okay, and so we have our unsteady diffusion equation here, and so we just have simply partial phi partial t is equal to 3 partial squared phi partial x squared. Okay, we have our boundary conditions, and so let's say that at x is equal to 0, but at all times t, then our boundary condition at the left side is going to be 1, and so we have a Dirichlet boundary condition there. But on the other side of the domain, where x is equal to 1, we have a Neumann boundary condition where the derivative is set equal to 2. Okay. And we also have our initial condition as well. And so our initial condition specifies what the solution looks like at t is equal to 0. Okay. But for now, and this is fairly common for a lot of codes, we're going to use what's called a 0 initial condition, where we assume that the solution starts at zeros everywhere. Okay. And so let's specify our domains. Okay. Okay, so first let's specify the time step size. And so that tells us, how much time is going to elapse in between our frames. And so we're going to use 0.1 seconds. Okay. Okay. And we're also going to use a grid of 5 points. And so we're only going to use 5 points to discretize our domain. Okay. And so this tells us that our grid spacing delta x is equal to 0.25. Okay. Okay. And so, you know, when you're working with time stepping problems or unsteady problems, you have multiple spacings to keep in mind. So you have the time step size, and also the grid spacing. So make sure you kind of write all those things down just to kind of keep it organized, because it is easy to mess up because they're both deltas in the roadway. Okay. Any questions on the setup for the problem? Okay. All right, so let's go ahead and, you know, we went through the trouble of deriving this, so let's just go ahead and plug into our explicit Euler equation. Okay. And so for this particular problem, we have a diffusion coefficient of 3, right? And so the diffusion coefficient is the number that's in front of our diffusion derivative, okay? We have a velocity, convection velocity of 0, right? So we have no convection term here at all. Delta x here is 0.25. And delta t here is 0.1, which is given to us in the problem. And I believe that's all we need. Yeah, so that's all we need. Okay, and so if we plug all these in, then we get the following equation. Okay, so we get phi I n plus 1 is equal to 4.8 phi I minus 1 to the n minus 8.6 phi I n plus 4.8 phi I plus 1 n. Okay. So not that different yet, and so we've you know, we've done this before, and so we've taken our finite difference approximations, we plugged in our parameter values for it, and we got an algebraic equation. So all that's new, okay, or all that isn't new. What is new is what we're actually going to do with this. Okay. And so first, let's go ahead and apply this for all the interior nodes. And so our interior nodes here are nodes 2, 3, and 4, right? So we only have a 5-node grid. And so phi 1 is going to be our left boundary condition. Phi 5 is going to be our right-hand side boundary condition. And so for nodes 2, 3, and 4, we use our finite difference equation for this. Okay. All right, so for index 2, we have phi 2 at n plus 1 is equal to 4.8 phi 1 at n minus 8.6 phi 2 at n plus 4.8 phi 3 at n. Okay. And I'm just going to go ahead and fill in the rest of them as well. Okay. And so those are the time marching equations for nodes 2, 3, and 4. Okay, so for nodes 1 and 2, or 1 and 5, excuse me, we have our boundary conditions. Okay. And so for node 1, we have our Dirichlet conditions. We have phi1 is equal to, phi1 is equal to 1. Okay. And since the boundary condition does not change with time, I could go ahead and specify the time index to whatever I want. And so for now, I'm just going to set phi1 at n plus 1 is equal to 1. Okay. And then same for our Neumann condition. So for node 5, we have d phi dx at x is equal to 1 and t is equal to 2. Right. And so just like we did before, we're going to replace this with a finite difference in space. And so this can be phi5 minus phi4 all over 2 delta x is equal to 2. Right. And since this Neumann condition also does not change with time, it's valid at all times, we can set the time indexes a little bit arbitrarily. Okay. And so I'm going to do something that might look a bit weird first. And so I'm going to set the time index for phi5 to be n plus 1, and then the time index for phi4 to be n. Okay. And the reason I'm doing that is mostly just to make sure that we have an n plus 1. And so we need to have an n plus 1 term here. And I did this to ensure that we only have one n plus 1. Okay. And so the way explicit Euler works, you can't have more than one n plus 1 in the same equation. Okay. And so by doing this, I put an n plus 1 on phi5 and an n on phi4. And then we can again solve this for the n plus 1 term. Okay. And so if you move terms around, you multiply by delta x, what you get is phi5 n plus 1 is equal to 0.5 0.5. Can you put the n on phi5? No. So in this case, you need the n plus 1 on phi5 because we have an n plus 1 equation for phi4 already. And so because phi4 is an interior node, we use the finite difference equation for that. And so we need to put the n plus 1 on phi5 in this case. And I made a mistake. And so, because this was 4 difference, I accidentally put a 2 in the denominator there, but it should just be delta x. Okay? And so we have a phi5 n plus 1 is equal to 2, which is 0.5, which is the result of 2 times delta x. Okay. And then to that, we're going to add phi4 at phi4. Okay. All right. Any questions on this? Yeah.
There's no such thing as n minus 1.
No. So n minus 1 is kind of like old news. And so we when we solve these time marshalling schemes, we want to use the most kind of updated information to solve for the next time step. And so that's why we just use n. Yeah.
It means that n is always replaced. Like in every iteration.
Exactly. Yeah. So n is always going to be replaced. And so once we kind of get this rolling and you kind of see the algorithm in action, you'll see that the n is going to be replaced. And so as soon as we solve for n plus 1, that's going to be our new n, and then we're going to solve for the n plus 1 after that. Yeah.
Is it more complex, like solving backwards?
There are algorithms that solve backwards. So those are called leapfrog methods. And so they do exist. And so they use kind of the n minus 1 term in kind of a clever way. Together with the n term to make it more accurate, but that's a little beyond the scope of this class. But they do exist out there, and they do have their niche uses where they're really useful. Yeah. Mm-hmm. Yeah. But usually most of the time you just have n plus 1. Mm-hmm.
Oh, excuse me.
Yeah.
One more time. Why are you putting n plus 1 again?
Yeah, so we need an n+1 here because, you know, we're going to form a system of equations here which have, you know, an n+1 for all 5 nodes. And so we have 5 nodes, and so we need an equation for each one to get the n+1 value for that node. So we already have the n+1 equations for phi2, phi3, and phi4. And then for the first and last nodes, we use the boundary conditions to get that. And I kind of manipulated the n+1s to kind of make sure that we get an n+1 equation for phi1 and for phi5.
Is that just kind of like the general rule for every time we do this?
Yeah, yeah. And so you need to have an n+1 equation for every single node.
Okay,
Yeah. Mhm. Okay. All right. So let's go ahead and put this into matrix form now. Because we love matrices in this class, or more like MATLAB loves matrices. All right, but these matrix equations are going to look a little bit different than the ones we've had before. Okay, so on one side, we have our vector of phis. Okay. And so those are all the phi n+1s, and so that's why we need exactly one in every single equation. Okay. Then we have our vector of coefficients. And so this is going to look a little bit different than before, but let me go ahead and write these out. And so for the first row, we have 0, 0, 0, 0, 0. Okay. And then we have 4.8 minus 8.6, 4.8, 0, 0. Okay. Then this is going to be multiplied by all the phi terms. Okay. But these are going to be the phi terms at the current time step. And so at this time step n. Okay. And then to this, we're going to add all the extra terms. And so these are all kind of the boundary condition terms. Okay. All right. And so if you perform kind of the matrix vector multiplication and the addition here, you'll see that this matrix form of the equation is exactly the same as the 5 algebraic equation that we have up there. Okay, I just kind of extracted the coefficients to kind of make it a little bit more convenient for us to implement in MATLAB. Okay. Right. So before we actually start using this, let me just kind of make a reminder first that this phi vector here, represents all the solutions at the current time step. Okay. And so remember, the important thing about the solution at time step n is that this is known, and so this is already known for us at this point. Okay. Okay. And so the way that we're going to proceed is we're going to use this matrix set of equations right here. It's not really a set of equations. It's more just like an arithmetic equation. Okay. Because we're not going to be inverting anything, and so we're just going to be performing matrix vector multiplication. We're going to start by plugging in our initial conditions in for the phi n's. We're going to perform the multiplication, and then we're going to go ahead and kind of proceed like that. Okay. And so I'm going to do a couple steps here, just because it kind of gets repetitive, but I wanted to kind of illustrate to you how this is going to work. All right. Any questions before we before we get started with this?
Professor?
Okay. All right. So let's go ahead and see how this all works in action. Okay. So before that, let's kind of remind ourselves what our initial condition is. Oh, sorry. Is it muted?
Hi, Professor.
Oh, say again?
I had a question on the beginning. I couldn't see. I know you mentioned something regarding if you can scroll up.
Yeah.
So right here where you have right here, with the 2 equals the 5, 5, n plus 1. I know you said you kind of like switched it around so you can manipulate it to get that n plus 5.
Yep.
What did you manipulate again?
Yeah. So the reason I did this was just to make sure that we had an n plus 1 term here, right? And so if you look at all the equations that we've developed so far, and so we had the phi2, phi3, phi4, and phi1, they all had an n plus 1 term to them. The only one that we're missing here, and so if I were to draw out the domain like this, right? Right, so we have 1, 2, 3, 4, 5. The only one that we're missing so far is just phi 5 and n plus 1. And so the thing that I manipulated, because normally when you make your Neumann boundary condition, it just looks like this, right? And so you say the derivative of the solution at the end of the domain is equal to 2. And so you replace that derivative with the finite difference approximation, which is normally phi 5 minus phi 4 divided by delta x is equal to 2. And so what I manipulated here is where I put the time indexes. And so, we could have done something like this, right, where I put n on both of these. And technically speaking, that wouldn't be incorrect because this boundary condition is valid at all times. But I wanted to manipulate this such that I get a term with phi 5 n plus 1 so that it can kind of fit together with everyone else. And so that's why I put n plus 1 on the phi 5 and an n on the phi 4.
Why did you do it based off the, what was it? The delta x, which I was just looking at it because I thought it'd be cool to do the delta t based off time.
Yeah. So the delta x here comes from the fact that we have a derivative in space right here, right? So we have d phi dx, and so the only place where we had dt was when we replaced this time derivative here. And so when we replaced the time derivative with the with the finite difference, that's when we pop dt into the delta t in the denominator. But since our derivative here is with respect to space, that's why the denominator here is delta x. Yeah. And so it's the same reason why, for this derivative right here, this partial phi partial x, that's why I have this delta x in the denominator here. Yeah. But when you take the derivatives with respect to space, you still have to assign a time index for all the phis. And so for the boundary condition, I just did it a little bit more. I took a little bit more liberties with it just to make sure that we got everything that we need for the for our 5 equations. Yep.
Thank you.
Yep. Okay. And so our initial condition, remember, was the solution was all zeros, right? And so the way that we can state this is we can say that phi 1 is equal to 0, phi 2 is equal to 0, phi 3 is equal to 0, phi 4 is equal to 0, phi 5 is equal to 0. Okay. And this is all at the very first time step. And so this is when n is equal to 1. Okay. And so the very first operation that you're going to perform is you're going to replace this entire phi n matrix here with all zeros. Okay. And so you're going to replace that with all zeros. And so once you replace that with all zeros, then you just perform the matrix vector multiplication. Okay. And so you have this matrix here that's going to be multiplied by this vector. And so you have all zeros here. And so the entire first section here is going to be 0. Okay. And then what you have from there is you have just 1. You add the 1, the 0, 0, 0, and the 0.5. Okay. And so after one time step, our solution is, yeah. So these exponents here are 1s, and so that's to indicate the very first time step. Okay, so after one time step, our solution is V1 is equal to 1. Okay. V2 is equal to 0. V3 is equal to 0. V4 is equal to 0. And V5 is equal to 0.5. Okay. And since we advanced this one time step, the time index for all of these would be 2. And so again, to get these, to get the solution right here, all I did was I plugged in our initial condition in for the phi n's, okay, which is this vector right here. And then I just performed the matrix vector multiplication. And so since this vector here was all zeros, then I didn't have to worry about that first term, and I end up with just this guy. Okay. Right. So does that make sense? Or are there any questions about how I obtained these phi values here on the bottom? So that's after one time step. Okay, and so now that we solved this for one time step, let's go ahead and solve it for another time step. Okay, and so when n here is equal to 2, and so we kind of move on, our previous solution that we solved for, that now becomes our known solution. And so what I'm going to do now is I'm going to replace this with our solution that we just computed. Okay, and so since we just computed that phi1 at 2 is equal to 1, okay, and then phi5 at 2 is equal to 0.5, okay, then we're just going to run it through again. Okay, and so after 2 time steps, after 2 time steps, our solution is, okay. And so here we actually have to perform some matrix vector multiplication, and so we have this whole matrix of coefficients here, and we're multiplying by the vector 1, 0, 0, 0, 0.5. Okay, and so if we do that, we get phi1 is equal to 1, same as before because it's our Dirichlet boundary condition. Phi2 here is equal to 4.8. phi3 here is still equal to 0. phi4 here is equal to 2.4. And phi5 here is equal to 0.5. Okay. And so since this was solved after 2 time steps, all of the time indices here are going to be 3. Okay. Okay. Right. So that's the solution after 2 time steps, and of course you can kind of continue this logic kind of more and more and more. Okay, and so I don't actually have it computed, but I can tell you how to set it up for the next one. Okay, and so for the 3rd time step, what you need to do, just like we did for the last one, is we're going to replace this phi n here. Okay, this vector of solutions at the known time step. We're going to replace that with the solution of the time step we just computed previously. Okay, and so the time step we just computed previously is 1, 4.8, 0, 2.4, and 0.5. Okay, right, and then once again you're going to perform the matrix vector multiplication and then carry that through. Okay. And so this kind of just continues on until you kind of reach the number of time steps. Okay, and so usually the user is going to specify how many time steps that you run for, but you can, let's say that we want to run this for 10 time steps, and so we repeat this 10 times. Okay? But kind of the key step is this one right here. And so what I've circled in green is that you replace the values in this vector with the solution you computed last. Okay. Right. And so to sum it up, the way explicit Euler works, you generate this matrix of coefficients, you generate this kind of evolution equation. You start with your initial condition, and then you perform the arithmetic. You get the solution at the first time step. Then you take that solution at the first time step, and then you plug it back into where the known solution is. Okay. You carry it out again, and then you find the solution, and then you plug that one back in there. Okay. And so this whole thing kind of just goes on repeat for as many times as you want. All right. Any final questions on this before we wrap it up for the week?
This is with every time step we add the boundary conditions as well as.
Yeah, so the boundary conditions are already implemented. So the boundary conditions are already kind of baked into the first and last lines of this matrix. And so because we've already kind of baked it in, then we don't have to worry about manually specifying it again.
Can you show me like how you got those values for the second time step?
Yeah. And so you mean these ones down here?
Yeah.
Yeah, so the way I got them was I plugged in the solution after the first time step. And so that was 1, 0, 0, 0, 0.5. Okay. And so let me just focus on just this one. Okay, so phi 2.
Yeah.
And so phi 2, we're going to take a multiplication of this row and this vector right here. And so this row right here will be 4.8 times 1 plus minus 8.6 times 0 plus 4.8 times 0 plus 0 times 0 plus 0 times 0.5. And if you perform that arithmetic, you get 4.8, and that's how you get this guy right here. Yeah, so next week, I'll show you the MATLAB code for this, and so MATLAB's going to automate all this for you. But it's important to kind of show you guys how it's set up and kind of the logic behind this. All right, so thank you guys for coming this week. Remember our midterm is next Wednesday, but this time marching stuff is not going to be on the midterm, so you don't have to worry about it for that. Okay. So have a great weekend, everyone. Keep an eye out on Friday for the review video. So I'm going to record it Friday afternoon. And then hopefully that'll help you guys with your study. Okay, so best of luck studying, and I'll see you guys next week. Thanks, guys. Yep.
These solutions are just for time step, not for the next time step.
It's for so what you're going to be doing for these is that you're going to be saving these solutions kind of into a because before when we solved we just get one solution and then we would just split.
You get like 6,000.
But what we're solving for instead here is a series of so think of that like the first frame of the video. It should be like the second frame of the video. So you can solve it.
I had to do that.
You have 10 solutions or 10 frames. And you kind of just display all 10.
Just focus on
So then why don't we the boundary conditions for for the second time step rate plus 1 plus 1 since we're adding.
Yeah. So the boundary conditions are already kind of okay. So for the first node, we have a traditional boundary, right? So it's those are one. Notice how the first row in our matrix here is all zeros. And so it doesn't matter what this is right here, then the first key is always going to be 1. Because we take a row of 0 and we multiply by this vector. So this one's going to change. So P5 is going to change because it's a Neumann condition. So it's a derivative. And so that's going to depend on what this is going to depend on what this is.
Okay. Yeah. Okay. Thank you.
Yeah. Yeah. So that one value was from the phi4. And so remember our Neumann boundary condition was this equation right here. And so this 1 is meant to be for phi4. And so remember before we started plugging in stuff here, this was phi1, phi2, phi3, phi4, phi5. And so since we have phi4 here on the right side of the equation, then we need this 1 here to kind of reflect.
But it doesn't matter if it's like a phi n plus 1 or.
Yeah, so it's because it's phi n. So because it's phi n, it goes on this side of the equation. And so all the n plus ones get put over to the left. And so that's why the phi 5 n plus 1 here is right here. And then because we had a 1 phi 4, that's why it ends up.
Oh, okay.
Yeah.
All right, thank you.
Yep. Mhm.